Hey guys. Yeah, so hi Doris, Idris, and Oscar, Minglun, Chloe, and Walker. Okay, all of you, good afternoon. Oh, and Sean. All right, so what do we have today? Today we are gonna start something that's new called the network layer. All right, but before we start with the lectures, let me just bring to your attention this. We do have two quizzes during this Saturday, but they are both quite straightforward, and I think all of you will be able to complete these quizzes by the end of the lecture today. All right. One thing, this is more a gentle reminder, PA number 8. It's not due in this Saturday, it's due next Saturday. What I want to say here is that PA8 is actually a little challenging, and especially when you want to do it the complicated way, or you want to do it in a way that it works seamlessly with the web server implementation in Golang already. Okay, so PA8, not trivial. Okay, you want to start early. And of course, tomorrow is the second exam. Okay, so I've already finished writing the exam. My fear is that you guys might do too well, okay, with this exam. Uh, uh, Having said that, that doesn't mean that you then skip all the plan of studying later today. Okay, so you still want to study. So my assessment is that if you just study, make sure that every concept introduced is clear, then you should do well. Okay. And hey, Elaine. Okay, good, just in time to join us. And the first topic, of course, introduction of the network layer. Okay, so in this video, you will see that there are three major functionalities in the network layer. The first one is actually very similar to what we've seen before in the transport layer and the application layer. Right? From the application layer, you send message down to the transport layer. Transport layer will break a message into segments. Network layer getting the segments from the transport layer. Those segments will be broken into datagrams, all right? And then additional headers, the network layer headers will be appended, okay, over the datagrams. So that is the first major functionality. And then there are two more functionalities. One is called forwarding. The other is called routing. So essentially, once the network layer module in your operating system receive a segment, it's broken into datagrams, and the next thing is that the internet tries to find a route, okay, for these packets that's going to a certain destination. So that functionality is called routing. So once the route is there, these datagrams will be forwarded hop to a hop, router to the next router, to the next router, along the route finally to the destination, and that is called forwarding. Welcome to chapter 4, the network layer, and particularly the data plane. So in this chapter, the goals are understanding the principles behind these network layer protocols, and we'll focus on data plane and talk about the other one, the control plane, in chapter 5. So in the overview section, we're going to talk about the service models possible for these network layer services. And we'll talk about the main functionalities that people implement in the network layer. Forwarding and routing. We'll talk more about these. And we'll be spending some time here talking about the architecture of a router and how packets travel through a router. And the rest of the chapter will be spending a lot more time here talking about forwarding of packets generally, as well as how it's implemented, how it's working on the internet. 4.1, the overview of network layer. Well, what the network layer is doing is simply this: transport segments from the sending host to the receiving host. So let's use the micro internet here as an example. And let's assume this guy here is the sending host, and this guy here is the receiving host. So the goal of the network layer service is so that we could send segments or packets through the internet to the receiving host. Now, what's a bit special though, okay, in the network layer? It's not only the two end hosts have the network layer protocol implemented and operating our machine. Each and every router inside the network here would also have the network layer protocols running. Now to be exact, on the sending side, on the sending host here, the transport layer segments is going to be encapsulated into the datagrams. So a packet at the transport layer is called the segment. But when a packet now goes into the network layer, it's called a datagram. And sometimes also called the IP datagram. Okay, so transport layer, TCP layer. Network layer, IP layer. Transport layer, we have the TCP segments. Network layer, we have the IP datagrams. Okay, so at the sending side, we encapsulate these transport layer segments into the IP datagrams. Now these grams, datagrams will go on to the network and travel from router to router. And each of the router will examine something special, in the packet header, in the IP datagram header, and decide where to pass it further on. So that magic we'll talk about more in the sections to come. Finally, when the packet arrives at the receiving side, so this is the receiving host, the network layer is going to look at the datagram, remove the packet header, and pass the segment up to the transport layer. So that is the lifetime of a packet traveling the network through the network layer. So in NMA, so packet coming from above, pending the header, so packet gets a bit bigger, and you see routers busy forwarding the packet and eventually reaching the receiving host. And at the network layer header or the IP datagram header removed and the segment restored and pushed up to the higher layer. Alright, so that is the general picture of what the network layer protocol is doing. Now, the network layer protocol is doing two major functionalities. As you observed earlier, forwarding. The routers are all busy moving packets around from one router to another router. Hopefully, it gets to the next router that is appropriate so we don't take too much time to pass the packets until it reaches the receiving host. The other is this. This is also the magic that I was talking about. So this is the computation, the intelligence in the network layer that determines a route between a pair of sending host and the receiving host. Or a lot of times we just call them the source and the destinations. So to determine an end-to-end path to travel over the internet from the source to the destination. And that intelligence is also called the routing algorithms. An analogy is this. Let's assume the class is taking a trip to Canteen. I know the weather is getting warm. It would be really nice if we're in Canteen. Well, the thing you need to do first is this, routing. You pre-compute or you Google and come up with a plan for the day of travel. Whether we take a bus to the Taipei station or we take a metro to the Taipei station. And from the Taipei station, do we take a high-speed rail? And from the high-speed rail station at Kaohsiung, do we take another bus or do we all rent a car or rent a number of these bikes so that we ride along all the way to Canteen? So the computation process, the intelligence that we need to do ahead of the travel is called the routing. Now, on the day of travel, we'll bring this Google map printout saying, hey, you start from home, you walk to a particular station, and you hop on a particular metro line. And once you get to the Taipei station, you just hop onto, high-speed rail number 112. And then after arriving at Kaohsiung, you go to a particular bus stop, and then you hop on the next vehicle taking you to Canteen. So that is this forwarding. So at every interchange point, you look up a piece of paper and find out what is the next step to do. So this way, it ensures that the forwarding part, the traveling part is going to be fast and smooth. So the separation or the differentiation between the routing function and the forwarding function. So nowadays forwarding, you just probably open up your Google map, right, and look where's the bus stop next. So routing and forwarding. So in short, Chapter 4 is all forwarding. Chapter 5, all routing. And forwarding is in the data plane. Routing is in the control plane. So control meant that, the routes are being controlled, or calculated. And data plane meaning the datagrams are being forwarded, passed. So this next video is to tell you a little bit more about the separation of the two functions and into planes. You see, in network layer, The structure is interesting in a way that there's a control plane and there's a forwarding data plane. Okay, so the data plane is a little bit lower. What's being done is very straightforward. Take a data, take a packet, pass the packet, and simply that. And that needs to be done really fast. But in the control plane, you heard there might be a routing algorithm there going on and do the computation. And things can even be more complicated. After the computation, you might need to consider this and that and adding additional restrictions. Okay, so data versus control plane. In the video coming next, you will hear that there's a traditional way of control plane calculating routes and then setting up these tables to allow very fast forwarding of packets. But nowadays, the modern days, we have a very different way of doing control and how it interacts with the data plane. And that should make it a bit clear for you to see the separation between data plane and the control plane. So by data plane, we actually meant to talk about the forwarding function. Okay? And the control plane, on the other hand, is the routing function, the part that is trying to identify a path between the source and the destination. Now let's talk a bit more about the data plane. Okay, so what's being done there is very local. Each router is determining for each incoming datagram who should be the next router to forward it further. Okay? And that is the forwarding function. So it's illustrated here. For a datagram coming in, this router here is looking up a table and find out, oh, this should be the outgoing port and therefore reaching the next router. Now, the control plane, on the other hand, is the part implementing the routing functionality, okay, implementing the intelligence. It is to determine, okay, how would the packets be able to travel end-to-end from the source to the destination. So these routing algorithms will be implemented in the control plane. Now, there are two different approaches implementing the control plane. One is the traditional approach. The other is called the SDN approach. Okay? The traditional one is the distributed approach. And the modern one, the SDN one, is actually more centralized. Okay? To your surprise, isn't it? Okay, we are actually moving from distributed solution to centralized solution. Now, in the traditional one, each router will be implementing the routing algorithm, and the routers will also exchange information among themselves. As a result, and collaboratively, they calculate an end-to-end path. Now, in this centralized approach, in the SDN, we actually ask a couple very powerful machines, a couple very powerful SDN servers that are actually sitting far away from the routers to do the computation. And then after the computation is done, they're gonna install the routes back into the routers. So the tables are actually computed on the routers locally in the traditional way. But more recently, the modern way is to have some powerful machines computing all the routes and then install them back to the local routers. And local routers no longer do the complex route computation. So let's talk a bit more about the data plane. So this is the forwarding part. So this is the part implementing the per router action. And it's very simple, very fast. All that is done is the packet coming in, the router look at the specific packet header field and match to an entry in the forwarding table. So this is called the fast output interface lookup. Once we get a match, we get also the outgoing interface. Let me illustrate. So these are the routers. And inside the router, you see this is the entire operating system stack. There's this thing called the forwarding table, and each router will have one of these. When there's a packet coming in like this, it's going to look into a packet header field and matching the pattern here to the entries in the table. Now, we see that this guy is the matching entry. Therefore, immediately we see the packet should go out on interface 2. So output interface 2. So this is the direction to forward the packet further, and therefore next is going to arrive here in this router. So this is exactly the detailed step of packet forwarding in the data plane. And the control plane is here, higher up in the operating system stack. To be more exact, and let's talk about the traditional approach first, where the computation is distributed. So the routing algorithm is going to be running on each of these routers, and up here. The routing algorithm here, 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 and here. So each and every router okay, is going to have the routing algorithms running, and they're going to interact with each other. So there are these exchanges of messages, okay, between these routing algorithms distributed on the routers. Okay. And this is the control plane. As a result of the computation and exchange, okay, they find out what should be the forwarding table, okay, for different incoming packet, for different packets going to different destinations, and install the local forwarding table into the data plane. So this is the separation of the control and the data plane. Now, in the modern days, we take the centralized approach, the SDN approach. Now, it looks a little bit different, the separation of the data and control plane. So routers protocol stack, okay, stop right here, because the computation is all where? Up here, okay? A couple machines, powerful machines, okay, doing the computation. But it cannot be computing without information provided by the routers here. So these routers, okay, will have a tiny little process running here. They're called the control agent. The control agent here is going to provide input to the remote controller. This is the big process implementing the routing algorithm. So after collecting information about, hey, who they are and the connectivity of these routers to other neighboring routers, now this controller here can then do the powerful computation. Once the result is obtained, okay, those tables are communicated back, sent back to the control agent, and therefore installed into the data plane of the routers. All right, so you want to think about this network layer as if there are two sub-layers, right? The lower one, the data plane, the higher one, the control plane. Good. Next topic, the L3 service models. So L3 is actually the network layer, so layer 3. And the reason that it's a layer 3 is because we are actually counting from the bottom and up. Physical layer, the lowest one is L1. Right? And then data link, the second layer, and then network layer, the third. Okay, so relatively speaking, transport layer will be L4. Okay, so we're talking about the service models of the network layer. Okay, there are two models. One is called connectionless, the other connection-oriented. Hey, that happened to coincide with the two service models we see in transport layer, isn't it? There's TCP, connection-oriented, UDP, connectionless. Before we talk about the service models implemented at the network layer, let me remind you this. If you recall, when we were talking about RDT, we say sending process, receiving process. If the underlying channel is reliable, all they need to do is just to pass data out, and the data is just going to arrive. But unfortunately, the channel is not exactly reliable. Okay? And depending on how unreliable the channel is, the complexity, okay, of the reliable data transfer service is going to be different. More unreliable, more complex. Less unreliable, less complex. Okay? So the service model we'll be talking about next is to talk about how we implement. Okay? What kind of channel we're providing here. Are we going to provide a more reliable channel or less reliable channel? So more reliable channel is one service model. Less reliable channel is one service model as well. And we could actually have a spectrum of different service models here. There are two major camps of service models. First is the connectionless service. What it meant there is that the end hosts and the routers in the middle, they do not set up any connection-specific states before data being passed around. So there's no reservation of bandwidth, no reservation of memory space to buffer packets. Okay, so you see that there's not going to be any guarantee at all. Exactly. So this connectionless service is also called the best effort model. Okay, and this is exactly the model implemented in TCP/IP, the internet. The second camp, the connection-oriented service, which is the opposite. So the end systems, as well as the routers in the middle, they would actually exchange message and establish a connection before the data flows. Okay. So this is actually implemented in some of the old architectures, old systems. ATM, this is not the bank ATM machine, banking machine that you withdraw money. So this is actually a specific computer network that have been designed in the 20th century. At some point, okay, ATM is actually competing with the internet. I think towards late 90s, okay, still before the turn of 21st century, ATM gets merged into the internet. So some of these routers in the internet, the lower architecture design is actually from ATM. Now, Frame Relay, X25, these are just too old. Okay, but These are examples of connection-oriented network layer service. Okay. Now, to establish such a connection will involve routers, okay? And the involvement is actually quite deep. It's complicated enough. It's the third important function, okay, in these systems, on top of routing and forwarding. Now, one last bit I want to talk about is this. We've heard about connection-oriented service as well when we were talking about TCP, right? TCP, they're sending SYN ACK, and then ACK for the SYN ACK. Hey, that's establishing connection, right? It sounded very much like these, ATM frame relay X25 is doing. Yes. At the transport layer, TCP is actually establishing connection between two processes. At the network layer, in ATM frame relay X25, they are actually also establishing connections between two hosts. All right? But be careful. Internet at the network layer does not implement connection-oriented service. However, at the transport layer, implements connection-oriented service. So just be clear. Internet, the subject we're talking about and we'll continue to talk about, does implement connection-oriented service at the transport layer, but not at the network layer. Internet, in fact, when it is designed, it does have this complexity at the edge mindset so that we don't do complex things in the network layer involving the routers. All right, so L3 service models, generally two different models, but internet is just the connectionless model. All right. Now the next video is just to take you a little bit closer into the connection-oriented service. In fact, that even though we call it connection-oriented service in L3, but there could be different levels of connection-oriented services. Yeah, those are the major camps. But within each camp, you can probably define finer service models so that you provide different levels of service. So, for example, okay, we could actually come up with services for individual datagrams, such as guaranteeing the delivery of a particular packet, guaranteeing the delivery of a particular packet within 40 milliseconds. We could also try to provide services guaranteeing the flow of a number of packets. So we ensure that these packets will arrive in order, or we guarantee a certain bandwidth, okay? Or we restrict, okay, the time differences in between these packets when they arrive. So again, service models, they can be finer, okay, or coarser. It's more like a spectrum. Now what I'm listing here are the 5 services models that have been implemented and being used, at least for some time, okay, in ATM's case, and continue to be used today on the internet as well. So the internet service is, the best ever. So essentially it's not guaranteeing anything, okay, no guarantee at all, okay, and it's not giving condition feedback from the network layer. It's in fact being inferred from the transport layer, okay, between the TCP sender and receiver. Now ATM, okay, quite sophisticated, okay, provides actually a spectrum of service models. The CBR stands for constant bit rate service. So it actually guarantees a constant rate. So this is perfect for the constant data streams. It guarantees such that there's no loss, packet arriving in order, and the timing of the packets is also guaranteed. It's going to be constant. And there's not going to be congestion at all, so there's no need of congestion feedback. Variable bit rate service. Okay, so this is actually guaranteeing the maximum bandwidth required by a variable bit rate data stream. So there's no loss because we are guaranteeing to the maximum rate, right? So packet arriving in order, there's no delay as well, no congestion. Okay, so you see here, these two are highly guaranteeing everything, but one for the constant data stream, this one is for the variable rate data stream. Now these two, however, okay, available bit rate service. So this is only guarantee a minimum rate. Therefore, there could be losses and the timing cannot be guaranteed because there's a lower rate. Packet could arrive faster than they can go out. So they could get buffer, they could get dropped at the buffer. Okay. But in ATM, even though there's no guarantee of the bandwidth delay, but there will be explicit congestion signal back to the data source. And UBR, on the other hand, in ATM, so this is the minimum level of service in ATM. It's called the unspecified bitrate service. So there's no guarantee of bandwidth, no loss. Packet will still be arriving in order. That's special about ATM because it's, after all, still a circuit switch network. And there's no timing guarantee, and in this case, no longer a congestion signal going back to the data source. So you see, again, network layer service model, it can be a full spectrum. Just that unfortunately in internet, or fortunately in internet, there's just one model we talk about, the best ever. All right, simple for us. Okay, simple for Polly to explain internet's service model at the L3. Now, I think it's a good point to answer Mark's question about how often do we update the routing tables. That's a very good question. There are two ways usually. Sometimes when there's a route running into some trouble, they will be able to send signals out and therefore triggering the neighboring routers to recompute the routing table. So one way is triggered by external messages. Okay. The other is that these routers, very often they have this clock thing ticking, and periodically they try to recompute the routing table. Okay. So two ways, triggered or periodically. Now, good timing, isn't it? Let's take a closer look into what a router is like internally with the components. Now let's take a look into the inside of a router. This is the general architecture. We do have a processor, which is doing the routing algorithm. So the complex route computation is being done here. The processor is quite high-end, very much comparable to the CPU, high-end CPUs we're using these days, except that the processor here might be a bit more optimized for route computation. Second most important entity, the switching fabric. Well, people will argue this is probably the most important entity because this is the part of the router that is doing the actual switching, the actual moving of the packets. Okay? And we know that the packet needs to be moved very, very fast. So these switching fabrics definitely needs to be high speed. Third, the input and output ports. Okay? By output ports, input ports, I actually meant that these network interface cards, okay, that we use to connect to the routers that are passing data in, passing packets in, as well as connecting to routers, okay, that we pass the packets out. Okay. Now, you see then, yeah, the lower part is where the packets are flowing through. So this is the data plane, meaning this is the part of the router that we are flowing the data. So the functionality there, very important, just to move packets. In order to be very, very fast, yeah, the computation, the switching there is pretty much hardware optimized. And so they can work in this time scale, the nano time scale. On the other hand, the upper plane, that is the control plane. Now we have the routing algorithm implemented as software running there. So in addition to routing, it does also a little bit of the management of the router. Okay, for example, tracking, monitoring, how many packets coming in, how many packets going out, things like that. Okay. Now, this part being implemented in software then operates in a slower time scale, the millisecond time scale. Now, the one most important functionality for the router to do is forwarding. Now, it also does route computation here. Okay. Now, connection between the route computation and the forwarding here is this. After the route is computed, we install the forwarding table into the memory of the incoming network interface here. Let's zooming a little bit more into the input network interface so that we see a little bit more the forwarding functionality. Where does it happen? And it's happening right here. Okay, the component that's connecting the input network interface to the switching fabric. Okay, so what's being done there is essentially switching, and it's done in a decentralized way, meaning for each of these input port, each of these input network interface, there's a lookup processor. Okay? So the forwarding of packets coming into each of these input ports is done parallel across all these input ports. So that's what they meant here, decentralized. So each lookup processor here is doing this. It looks into the header fields in the packet, okay? And it's seeking the output port using a forwarding table that's installed from the route processor, and that is installed already into the input port memory here, okay, right here. So the goal here for the incoming network interface is so that it can complete, okay, the input port processing, the lookup forwarding, okay, at the line speed, okay, meaning, okay, if this is the speed of packets coming in, now this forwarding process needs to be fast enough so that we get the same output speed here. Okay. If this is slow and this is fast, so if this is R prime and R prime is smaller than R, then we'll end up having this. Okay. Packet gets queued. Packets need to wait somewhere in a temporary buffer before they can go out. So that's queuing. Datagrams, if they arrive faster than going out into the switch fabric, then there's queuing delay. Now, there are two different kinds of forwarding. In the traditional internet, we do the destination-based forwarding, which is to look at the packet header fields, particularly the destination IP address, and only the destination IP address. Now, in SDN, the modern routing, it's called the generalized forwarding because we can actually look at multiple header field values, not just one. And it can be arbitrary combination of these header fields. Okay. So it's a lot more general. But you can also see that provided the same lookup processor, okay, this is going to be a bit faster and this is going to be a bit slower. So in order to keep up the speed, okay, if the incoming is R and output is R prime here, in order to make sure this R prime is as high as possible, usually in SDN, okay, these SDN routers will need a faster lookup processor here. So this one here, SDN routers, more expensive, while this one here, usually more affordable. Alright, so wow, a router. Inside the router, you have many components. So next we will definitely talk about all the components. But the next video, let's focus on the forwarding table, okay, and the lookup process, because that's the key step there. Okay, key process there. We want it to be as fast as possible. Okay, this next video is called prefix matching because that destination address lookup is exactly doing this longest prefix matching. Very important video because there'll be back-to-back quizzes coming up next after. So that was the router architecture. Now, there's one thing I want to talk about which is very, very relevant to the rest of the chapter. Okay, destination-based forwarding. Okay, as you heard, forwarding is based on, for each packet coming in, look at the packet header field and try to match an entry in the forwarding table. Okay, so if the destination address says this, 11001000, matching this guy here, then we take this output port, okay, output link interface. If it matches, for example, this IP address, okay, then we take output port 2. What happened inside this forwarding table is, if you think about it, right, there are so many possible destinations on the internet. And for each destination, there needs to be an entry, isn't it? So this is this particular destination's output interface being 0. So in fact, okay, in a forwarding table, you should be seeing for each possible IP address, what is the output link interface? For each of these IP addresses, what is the output link interface? But the thing is this. Okay, how many possible destinations there can be? Well, the IP address is this big. Okay, the IP address, 8 bits, 8 bits, 8 bits, 8 bits together, 32 bits. So you could have actually 1 gig entries. Okay, and each entry might require, you see, 4 bits. 4 8 bits. That means at least 4 bytes, and maybe another byte here for the link interface. So each entry here at least needs to be 5 bytes. So 5 gig, 5 bytes, and that would be 5 gigabyte at least, just to keep the forwarding table. Okay, so the input port network card there, okay, it's going to require not just a high-speed lookup processor, but also a lot of memory space. In addition to the buffer space might be required, right, in case queuing occur. So that particular interface there is already very costly. And if you need to have many input ports, many output ports, think about the cost of a very high-end router, very expensive. And that's not going to scale very well if we actually, expand the IP address space. So this is a 32 bits IP address. This is IP version 4. Later on, you'll see. Okay, there's another version of the IP layer protocol. That's called the IP version 6. And the address space there is actually expanded to 28. So this approach, each IP, each entry, is not going to scale very well. So what's really being done on the internet is this. We do matching, all right, but not match the entire IP address. We only match the prefix, okay, of the IP address. So we're doing there doing table lookup is to do matching, but we are only matching to the longest prefix. Okay. So this is what we do when we're looking up in the forwarding table entry. So given the destination address, okay, so we'll take this address and match the entries here. Okay. This time we don't have one entry per IP address. It's actually an aggregated or the prefix. So what you're seeing here is we only specify the first part of the IP address and leave the rest general. Okay. So that is also saying that as long as the destination address, the first few bytes match this pattern, okay, the rest of the IP address can be general, free. Okay. Now, as long as you have a destination IP address looking like this, then we take this packet to this output port. And the second entry is saying that, okay, if the IP address matches this pattern, the rest can be flexible. No matter what, we go to output port 1. Right. Now, there could be multiple entries. For example, this guy here and this guy here, you see here. Oh, up to this point, they are the same. So you could have an IP address matching both entries, isn't it? So in this case, we'll take the longest prefix. Okay, we'll take the entry that the destination IP address matches the longest. Okay, now, in case the rest of the 3-bit of this IP address is 000, then we forward that packet to output 1. If it's something like 101, then it does not quite match this entry. However, matching this entry, then we send it to output 2. All right. So let's exercise a little bit. Now, if we get a packet, the destination address is this. What should be the output interface? Let's see. The first 8 bits match. Great. In fact, all these 3 entries, the first 16 bits, actually 19, 20, yeah, the first 20 bits are all the same. So these two destination address, I think the first 20 bits are also the same. So what differs is beginning from the 21st bits. So which entry in the forwarding table does the first destination address match? Well, this is 0. So only this entry match, right? Because this is 1, this is 1. So these two not matching. Therefore, this packet goes to interface 0. Now, the second destination here. Oh, 21st bit is 1. So it should be either one of these. Now, 0, 0, 0. Well, it actually matches more the second entry. Therefore, the outgoing interface for the second destination address being 1. And that takes us to a double quiz time. All right, so before we start with the quiz, just so that you know, if we keep the forwarding table such that there's 1 entry per destination address, it's not only that you need a lot of memory space to keep the table, but also that having a lot of entries to do lookup, it will also take a longer time. See? Now, quiz 30. Okay, so let's exercise longest prefix match. Okay, so you see here, this is the forwarding table, and for each of the prefix, there's a corresponding interface for packets to go out. So if these 3 don't match, then it will then match the otherwise entry, and we go out to interface 3. Okay, now Q1, Q2, Q3, and Q4 are just giving you 4 different destination address, and you tell Polly which interface the first destination address goes, and which one for the second and third and fourth. Okay, now let's move to W12 quiz 30 channel, and this should be straightforward. Oh, okay, you don't need time really. I see. Okay, so team 3. Oh wow, amazing. Okay, team 3 says 0, 3, 1, 2. Let's see. Okay. Team 7, 0, 3, 1, 2. Yeah, it does, right? So I guess the first 2 octets match perfectly. So we can kind of ignore the first 2 octets. Okay, the first 16 bits. And this is 0001. 0001. Oh, okay, so all 3 prefixes match to this point. And then the next bit, the 5th bit, is 0. So only the first entry match, isn't it? So yeah, Q1 goes to interface 0. Okay. So I guess it's very straightforward. All right. Now, why don't we move on to quiz 31? Okay. So now we are having the detail forwarding table. Can you regenerate this detail forwarding table such that it shows in a prefix fashion? Okay, compact prefix fashion. All right, so let me go to W12 quiz 31 channel. So let's see the score. Yeah, so quiz 31. Yeah, convert. So how do you read this? Let me come back here. How do you read this? Yeah, so all these destination address from 1000 all the way to 10001111, all these destination addresses go to interface 0. Okay, and for the second entry, you want to merge all these destination IP addresses. So write the part that is fixed, and for all the other parts, you use the star to represent it's free. Okay, good. So now the score. Yeah, so for this quiz, how about 3 minutes? That should be enough. Okay, oh wow. Okay, that might be a little bit too long than needed. Okay. So 3 minutes, let's see. I know the time-consuming part is probably make sure that you copy the 110 patterns down correctly. Okay, so take your time. Right, time's up. Yeah, I think you guys have got it. Yeah. So Minglun is the fastest. So this matches not only the first 3 octets, but also the first 4 bits of the last octet, right? And this is matching first 2 octets and the first 2 bits of the 3rd octet. And this is matching all first 24 bits. Okay, great. So I think, yeah, you guys are just busy typing things up. Good, you got it. This is longest prefix match and how the forwarding table is generated so that it's compact. Okay, but guys, this longest prefix match is for the traditional forwarding control. All right, for the general, the modern forwarding control, the matching can be a lot more general, not just matching the destination address, but many other fields, okay, in the packet header. All right. So to close today, there's one summary video, okay, closing everything up. Longest prefix matching is really nice because you see in the forwarding table, there are so many less entries, right, as opposed to 2 to the power of 32. So memory requirement at the input port, less. Lookup process, faster because, again, less entries to look for. So less memory, faster lookup, 2 benefits. There's one more benefit that justifies why we use longest prefix matching, but we'll talk about that later in section 4.3, IP addressing. Now back to longest prefix matching. If you recall, we say in the lower part of the router, the data plane, what we do is to often use hardware to optimize all sorts of processing there. Longest prefix matching is performed this way, also using a specialized hardware called the TCAMs, ternary content addressable memories. Okay, the idea of this is this. It's not strictly a memory space. It's actually memory space with some computation circuitry. So the main circuitry there is a searching interconnected network. Provided the destination address, which is a prefix, this searching network allows it to go really fast and go to an exit point where the output port is stored. Okay, so the searching circuitry is fired really quick, okay, taking the exit in 1 clock cycle. Now, the part that is a bit slow is to insert the right port number at different exit points. And that is done when the routing processor finishes computing the route, when we're installing the forwarding table. So the installation of the forwarding table there using TCAM is to install is to assign the right port number at different exit point in this searching interconnected network. And that is why when packet comes in, the searching part is really, really fast within 1 clock cycle. Okay. So the forwarding table installation is only 1 time, so it's not a big deal, okay, although longer. But for all the packets coming in, that's very, very frequent, very fast. Okay. Now, as you can imagine, TCAM is very expensive. Okay. Cisco Catalyst series there allow us to store 1 million of these prefix entries. So very expensive router. And by the way, Cisco is one of the biggest router designers, router manufacturers. There are actually a number of these router manufacturers in Taiwan as well, like D-Link, like Asus. Yeah. But the routers manufactured in Taiwan are usually lower cost, okay? Good enough for maybe home use, maybe for access point use, maybe for enterprise use. All right, so you see that not only we use longest prefix matching to make lookup very, very fast, we also use special hardware, okay, where we spend more time organizing these prefix matching entries when the routing table is installed, okay, so that later on the lookup is only just 1 instruction, super fast. But by the way, this TCAM, this memory with special architecture, is very expensive. All right, so with that said, I say goodbye, and I'll see you tomorrow morning for the exam. All right, so bye. Oh, by the way, I think I owe Glady the answer to his question. Yeah, sorry. So, hey, Ethan, sorry, I need to answer Glady's question. Yeah, so Glady was asking if the neighboring router tells wrong information, would that influence computation of the routing table? You know what? It does, okay? But it really depends on the routing algorithm used, okay? For some routing algorithms, such misinformation can be detected by a router by checking information received from the other neighboring routers. Okay. But for some routing algorithms, such misinformation will ended up such that the routers are forwarding data to the wrong routes. Okay. And potentially these routes can have a loop inside, and so that the data never gets to the destination. Okay. And it also depends on the misinformation itself. Sometimes the misinformation is easy to correct by the routing algorithm itself, but it will take some time. Okay. And some misinformation, it might take a long time, okay, until the true route are re-obtained. Okay, so yeah, so bye. Let me play the music now.